Welcome back to the Deep Dive, where we crack open the dense technical reports and complex engineering documents so you can absorb the critical insights and stay ahead of the curve. Today, we're diving deep into one of the most exciting recent releases in the open AI ecosystem, the Nemotron 3 Nano 30B A3B.
And this isn't just another model release. I mean, a deep dive here is absolutely necessary because Nemotron 3 Nano, it fundamentally shifts the conversation. We're moving away from just brute force scaling and towards mastering efficiency, specifically for agentic AI systems.
Agentic systems, right?
Yeah, we're looking at a system that's been engineered from the ground up to handle these complex multi-step workflows. I mean, that's the backbone of future autonomous agents.
So our mission today is pretty clear then. We need to extract the technical genius behind this efficiency. We've got sources covering the novel hybrid architecture, the colossal pre-training data campaign, the alignment, all of it. And here's the hook, the thing that really anchors everything we're going to discuss. Nemotron 3 Nano achieves up to 3.3 times higher inference throughput than similarly sized open models. That's a massive claim.
It's a staggering performance gain, and it's the direct technical payoff of a very aggressive architectural choice. They've gone with a novel hybrid design that combines the structural efficiency of mixture of experts, or MoE, with the sequential data handling strengths of a Mamba-Transformer setup.
So it's a blueprint then?
It's a blueprint for maximizing intelligence while minimizing latency in production. It really is.
Okay, let's unpack this and start exactly where the magic begins. The architecture itself. We really need to understand how they achieve that unbelievable efficiency number. So Nemotron 3 Nano, nominally it's a 30 billion parameter model, but it's doing something pretty radical under the hood that separates it from standard transformers. It's a hybrid design. What does that core Mamba-Transformer hybrid structure actually look like, layer by layer?
Well, the Nemotron series has been pioneering this hybrid path for a bit now, and Nemotron 3 Nano, it builds on the previous generations by weaving together layers from Mamba-2, that's the structured state space model, with more traditional attention mechanisms.
Specifically grouped query attention, right? GQA.
Exactly, GQA.
Yeah. Okay, but wait. If GQA is already a standard proven way to make attention computationally lighter, why go hybrid? I mean, wouldn't sticking with either pure transformer layers or a full Mamba implementation, simplify the whole training and deployment stack, wouldn't that yield similar gains? What's the trade-off that makes combining them necessary?
That's a really critical question. The core architectural insight here is that neither pure attention nor pure state space models are optimal for all tasks. They just aren't.
Okay.
Attention, so GQA in this case, it excels at capturing global dependencies across the entire sequence. That's absolutely vital for deep multi-step reasoning. But Mamba-2 layers, they are exceptionally fast at sequential processing. So handling long context, high throughput generation, Mamba is just more efficient, especially when the context you need is local.
So by interweaving them, you're getting the global reasoning power of attention only, where you absolutely need it, and then you're getting the raw speed of Mamba everywhere else. Is that the idea?
That's exactly the idea. The model has 52 layers in total.
52?
Yeah, and the specific interweaving pattern dictates the whole flow of information. You're maximizing computational efficiency by using Mamba for high-speed linear operations and then reserving the more expensive but more powerful GQA layers for that global information integration.
It sounds like a very smart resource allocation strategy, just built directly into the model's DNA.
It is.
This hybrid nature, it leads us directly to what I think is the most remarkable statistic in the entire report. The active parameter count. The model is 31.6 billion total parameters. That's a massive size. But its runtime cost is drastically lower. How low are we talking, and why is that so important?
This is the genius of architectural sparsity combined with MoE. So out of that 31.6 billion total parameters, only 3.2 billion are actively engaged in any single forward pass.
3.2.
3.2 billion. And even if you include the embeddings, that number only rises slightly to about 3.6 billion active parameters.
Wow. That's less than 12% of the total parameter count being activated. So,
yeah.
So we're getting the representational breadth, the deep knowledge storage of a 30 billion parameter system. But the computational latency is closer to a 3 or 4 billion parameter model. That's an astonishing ratio for inference.
And this is where we really need to do a neural signal check.
Okay, let's do it. Why does this really matter at a technical level?
Because this development, it fundamentally redefines the relationship between model intelligence and deployment cost. Sparse activation is not just a marginal optimization. It allows hardware teams to provision resources based on the active size, not the total size.
Right.
So for data centers, for enterprise deployment, this means you can run frontier-level intelligence on hardware that was previously reserved for much, much smaller models. It basically democratizes large model performance by just crushing the cost of inference.
Okay, so the MoE implementation is clearly the engine driving that sparsity. Instead of a traditional dense feed-forward network, they're replacing them with these sparse MoE layers. Let's drill down into the granular details of how Nemotron 3 Nano actually implements MoE.
Right, so the mixture of experts layers, which follow Shazir's original work, there would allow the parameter count to balloon without a proportional increase in latency. Instead of one big FFN, you have many experts, and the model only calls upon a select few for any given token.
And the sources give us a specific ratio for this model that really highlights the extreme specialization.
They do. They use what's called a granular MoE architecture, which employs shared experts. It's a technique that further refines how knowledge is compartmentalized. The total number of routable experts available per layer is 128.
128. That's a huge, specialized library of knowledge.
It is. But for any single input token, the model activates only 6 experts.
6 out of 128? That sounds like an extremely high degree of specialization. If you look at that layer choice, what does that imply about the model's learning philosophy? Is it betting on extreme domain expertise in specific tasks?
I think it implies that the model has learned these highly distinct, specialized functional units. So when it's processing a piece of Python code, for example, it might activate 6 experts dedicated entirely to, parsing control structures and handling syntax. But then a question about quantum physics activates 6 totally different experts dedicated to mathematical formulation and theoretical context.
And the reliance on only 6 suggests the routing mechanism has to be incredibly precise, confident in its selection.
Exactly. The selection itself is handled by a standard learned MLP router, which uses sigmoid gating. The router takes the token representation, predicts which 6 experts are most relevant to processing it, and then passes the computation only through those 6.
So that's the mechanism that ensures high accuracy, because the knowledge base of 128 experts is vast, while still maintaining that 3.2 billion active parameter budget.
That's it.
What other architectural tweaks did they include to maximize this efficiency and sort of cleanliness?
Well, they optimized across several standard components. They used RMS norm for normalization throughout. A specific technical choice was using the squared ReLU activation function within the MoE layers.
Which is often found to improve convergence speed and stability in these deep MoE architectures, right?
Exactly. And crucially, they adopted a strategy of elimination. They removed positional embeddings, they eliminated dropout entirely, which is a pretty common move in these massive stabilized models, and they avoided bias on linear layers.
Okay, removing positional embeddings is notable, especially given their focus on a 1 million token context length. How do they handle long-range position without them?
They're relying entirely on the sequence order that's inherent in the Mamba state space structure and the relative positioning that's captured implicitly by the residual connections and the attention mechanism itself.
I see.
And by explicitly untying the embedding and projection weights, they gain another minor degree of freedom in parameter optimization. All these small, clean, technical choices, they add up to an architecture that's just designed for maximum inference speed right out of the box.
And all this architectural engineering, the hybrid Mamba-MoE structure, the specialized sparsity, it all culminates in one metric: inference throughput. What are the key performance indicators that prove this architecture actually works in production?
The direct comparisons they provide are incredibly compelling, especially when you simulate these demanding real-world agentic tasks. We're looking at a scenario of 8K input tokens and 16K output tokens. This really tests a model's ability to read complex context, reason deeply, and then generate a long, articulated response.
Yeah, that 8K, 16K setting is a perfect reflection of a modern agent workflow. You ingest a large document, the 8K, and then you write a detailed report or a complex code plan, the 16K.
Exactly. So in this critical generation-heavy scenario, Nemotron 3 Nano delivers 3.3 times faster inference throughput compared to the leading competitor, Qwen 330B. It's also 2.2 times faster than GPT-OSS20B. These numbers aren't just marginal gains. They demonstrate a real step function change in operational speed.
And where were these benchmarked? We need to be sure we're comparing apples to apples.
They anchored the measurements on a single high-end production card, the H200 GPU, and crucially, they didn't just run their model on the best framework. They ran all the benchmarks benchmarks using the best possible configuration available in the two leading inference frameworks, so VLLM and TRT-LLM.
So they made sure any model they compared against was also running in its peak optimized state.
Right, no sandbagging.
And beyond just raw speed, there's also the efficiency of the tokens generated, particularly those internal thinking tokens that are so crucial for agents.
Yes, the efficiency is multiplicative here. Compared to the previous generation, Nemotron 2 Nano, this new model achieves up to 4 times higher overall token throughput. And, more importantly for cost control, the model reduces the generation of those reasoning-specific tokens, the internal thoughts, by as much as 60%.
60%.
Which means the model is getting to the answer more directly. And that dramatically lowers the computational cost and the latency for any system that relies on those verbose reasoning traces.
That reduction in redundant thinking, that's the crucial cost lever for enterprise deployment. You get the benefit of complex font generation, but at a fraction of the cost. It makes agentic workflows dramatically more viable in high-volume, low-latency environments. This architectural mastery really is the core story here. Okay, so architectural efficiency gets you speed, but speed is nothing without brains. And Nemotron 3 Nano's intelligence didn't come cheap. It was forged in an astronomical, highly engineered data furnace. Let's look at the training pipeline.
The scale is just immense. The model was pre-trained on a staggering 25 trillion tokens of text data.
25 trillion.
Yes, and this corpus was meticulously sourced, spanning 15 distinct categories to ensure both diversity and depth.
And the data curation effort was continuous, wasn't it? They didn't just recycle old data.
No, absolutely not. They estimate they added over 3 trillion new unique tokens compared to the Nemotron 2 corpus. That continuous replenishment of the data lake is just vital for preventing the model from stagnating on dated knowledge. The corpus included data up to a cutoff date of June 25, 2025.
And the curriculum approach they used shows they were careful not just about volume, but about when the model saw certain data. Can you walk us through the 2 phases?
Right, the 2-phase curriculum. It's designed to balance broad language acquisition with specialized knowledge refinement. Phase 1 used the lion's share 23.5 trillion tokens. And that was dedicated to a diverse mixture: general web crawl, multilingual text, code, academic papers. This phase establishes the core linguistic and foundational knowledge.
So phase 1 is about making the model a generalist, getting that broad coverage before phase 2 comes in and sharpens the focus.
Precisely. Phase 2 comprised the final 1.5 trillion tokens, and it started very late, only at the 94% point of training. Here, they strictly prioritized only the highest quality, most knowledge-dense datasets, things like specialized Wikipedia subsets, STEM SFT data, highly curated academic material. The model has already learned how to learn, and now this phase imbues it with deep, specialized technical knowledge in a very compact period.
Beyond the data mix, the training regime itself speaks to the massive scale. We don't need to recite all the specific betas, but what characterized the learning rate schedule?
They used a warm-up stable decay schedule, or WSD, which is optimized for runs measured in the trillions of tokens. The learning rate warmed up over about 8.4 billion tokens, reaching a peak of 10 to the minus 3. The crucial part, though, is the stability phase. That peak was held stable for 20 trillion tokens.
20 trillion, so 80% of the entire training time.
Exactly. Only then did it decay over the final 5 trillion tokens.
That massive stable phase, it suggests extraordinary confidence in the purity of the data, and a belief that the model needs an extended period at its peak exploration rate to really absorb the complexity of that corpus.
It implies maximum stability and deep exploration. They used the AtomW optimizer with optimized settings and maintained a gigantic batch size of 3072, which results in roughly 25 million tokens being processed per batch, given the sequence length of 8.N192. That level of parallelization is just necessary to make a 25 trillion token training run feasible within a reasonable timeline.
All right, let's move to the secret weapon, synthetic data generation. This is where they didn't just filter the internet, they engineered new training material, starting with the code pipeline, Nemotron CC code W1. Why is code acquisition such a tricky technical problem that it required tools like links?
Well, code fidelity is just paramount. When code is embedded in web pages, standard swapers often mangle the essential structure, indentation, line breaks, white space, all of which are vital for programming language syntax. So by using links, which is a text-based browser, they were able to reliably render the raw HTML and preserve that critical structural layout during the conversion to text tokens.
So links acts as a guardian of structural integrity. Once the code is rendered, they then used an LLM 5.4 to clean it up. What was the 5.4 model's specific job?
Its job was surgical removal of noise. It aggressively stripped away boilerplate, excessive commenting, surrounding natural language filler, while being hyper-strict about retaining all critical technical elements, the actual runnable code, API references, mathematical expressions. The pipeline then standardized all the equations into clean LaTeX format, and this results in a massive, clean corpus of over 427 billion tokens, which ensures the model learns only from functionally correct examples.
Then came the augmentation stage, Nemotron pre-training code v2, where they use techniques like rewriting and transpilation. Why rewrite code that's already been cleaned?
Because this moves beyond just cleaning to improving the code. They used Qwen332b to generate synthetic natural language and code dialogues, things like Q&A, code reviews, student-teacher interactions, all grounded in the core data. This teaches the model conversational code reasoning. The rewriting phase, using style-guided and self-contained optimization rewriting, aims to produce syntactically varied and often more optimal versions of the source code.
That seems risky. You're using an LLM to generate training data about complex code, which could easily introduce errors. How do they ensure quality control?
Quality control was absolutely crucial. Every single synthetically rewritten file was subjected to a post-processing check using traditional tools, specifically the Pilot Python linter. If Pilot flagged a syntax error, the sample was removed. This is a brilliant compound approach. You're leveraging the creativity of the element for augmentation, but grounding the output in traditional deterministic validation tools.
All right. And the transpilation translating Python to C++ tokens was the goal there.
They found that training on the Python source files that were translated into C++ tokens by Qwen332b significantly improved the model's downstream C++ code generation accuracy. It suggests that exposing the model to the equivalent concepts, but represented in different, structurally rigid languages, enhances its fundamental understanding of computational logic, regardless of the target language.
That's a huge lift in domain specialization. But they also created this novel concept crossbreeding pipeline called InfiniByte. This sounds like an effort to eliminate conceptual blind spots.
InfiniByte is designed to counter the limitation that traditional datasets often contain very similar bounded problems. It crossbreeds concepts from disparate datasets, competitive coding, advanced math, physics, chemistry, to generate complex, entirely novel programming problems that the model has never seen before.
So it's synthesizing new high-difficulty exam questions on the fly.
Essentially, yes. The two main strategies were obfuscation. So, reframing a core problem using terminology from a different domain and complication, which is genuinely making the problem multi-conceptual. It requires the integration of knowledge from 2 or 3 separate fields to solve. The output of InfiniByte isn't just theory, it's about making agents robust against novel problems they haven't seen before, which is essential for real-world deployment.
And finally, under pre-training, they reinforced core reasoning using the Reasoning Question Answer, or RQA, dataset. What was unique about this two-step generation process?
RQA, at 31.7 billion tokens, was designed to challenge the teacher model as much as possible. First, they filtered seed documents to ensure the base content was undergraduate or graduate level and required high-level Bloom's cognitive domains: analyze, evaluate, and create.
That's already pushing the boundaries for complexity right there.
It is. Then came the two-step generation using the powerful Qwen3 teacher model. Step 1. The teacher generated a difficult question based on the context, but with the strict constraint that the question must be answerable without the original context.
Which forces the question to be self-contained and reasoning-intensive.
Exactly. And for step 2, the same teacher model then answered its own question, but the original source context was deliberately hidden from it. This two-step process functions as adversarial self-improvement built right into the data pipeline. The teacher model essentially proves it has mastered the underlying reasoning by successfully creating a standalone hard problem and then solving it independently. It guarantees the RQA data is concentrated reasoning material.
Let's shift briefly to context length. Nemotron 3 Nano supports an astounding 1 million tokens. How did they train the model to handle that extreme length without suffering context erosion or forgetting its core skills?
Achieving that 1M-Token context length was handled through a separate long context phase, or LC phase, at the very end of pre-training. They used continuous pre-training, or CPT. They reused and scaled existing document QA data by 3 times and blended in synthetic retrieval-focused data.
CBT is generally slow and steady, right? Usually with a low learning rate, designed to gently introduce new skills without erasing old ones.
Exactly, using a learning rate of 10 to the minus 5. However, they ran into a classic problem. Optimizing exclusively for long context tends to degrade short context benchmarks. Training only on 512K sequences resulted in measurable drops in performance on tasks like MMLU Pro and Code. The model became great at long-range retrieval, but lost its fundamental knowledge proficiency.
So the solution wasn't just maximizing the sequence length, but maintaining the balance between scales.
That was the technical breakthrough. They shifted to a curriculum approach within the LC phase itself. They trained using a mixture of 512K sequences and short 4K sequences. This mixture successfully improved both the short context scores and the long context metrics.
So it taught the model to utilize the full context capacity efficiently while retaining the sharpness needed for quick, short-answer knowledge tasks.
Yes, and the results speak for themselves. Their Ruler 100 scores, the standard for long context retrieval, achieved up to 86.34% at the full 1M-Token length. It just proves that context extension requires a sophisticated training approach, not just a hardware bump.
Okay, Nemotron 3 Nano is an engine for agentic AI. The true mastery for this application happens during the multi-stage post-training. This is where the focus shifts from general knowledge to reliable, controlled behavior using supervised fine-tuning and advanced reinforcement learning.
Right. The sophistication of this alignment phase is really what differentiates an intellectual LLM from a reliable agent engine. It's all about teaching control, tool use, and efficient reasoning paths.
The SFT stage was highly focused on multi-step, multi-turn agentic tasks. But the key innovation here was designing the SFT data to embed control over the reasoning process itself. How did they achieve that reasoning on-off and token budget control?
This is so critical for practical deployment. They essentially baked control commands right into the training data. For reasoning on-off control, they randomly stripped reasoning traces from 10% of samples, so the model learns that when the reasoning trace is absent in the input, it should skip its internal thinking and go straight to the answer.
And vice versa when the trace is required.
Right. And the token budget control is even more important for a high-throughput system.
Absolutely.
They randomly truncated 3% of the reasoning traces to different budget lengths before the final answer. This forces the model to learn resilience, to produce a high-quality answer even when its internal thinking time, its token budget, is limited. It's the difference between an agent that always runs a deep, slow trace and one that can switch to fast, heuristic thinking when latency demands it.
That budget control is essential for managing latency spikes in real-time agent deployments. They also focused heavily on teaching tool-integrated reasoning using teacher models.
Yes. They used models like GPT-OSS-120B to generate highly structured reasoning traces that explicitly incorporated tool calls for tasks like competition math. This ensures the model learns the logic of tool use, not just the syntax.
And they made a simple but important technical choice regarding the formatting of those tool calls, using XML-style tags.
Yeah, they adopted XML-style special tags for tool calling, precisely to reduce character escaping issues that plague systems relying on JSON or other delimiters. Cleaner tags mean the model produces outputs that are more reliably parsed by the agent orchestrator, which just reduces system-level errors.
The breadth of agentic data sources is impressive. It covers everything an autonomous workflow might need. Multi-turn conversational tool use, software engineering tasks, handling GitHub issues.
And all of this synthesis was only possible because of a robust quality filtering pipeline. It wasn't enough to generate the data, they had to vet it. This pipeline included structural checks, like for malformed tool calls, pathological filtering to remove low-quality repetition, and crucially, LLM judge-based filtering.
What does the LLM judge filtering add that structural checks would miss?
The LLM judge ensures compliance and quality beyond mere syntax. It removes responses that are technically correct but low quality, inconsistent, or display unwanted model idiosyncrasies. It serves as the final semantic quality gate before the data enters the SFT set.
Okay, we now move to the reinforcement learning stage, RLVR reinforcement learning from verifiable rewards. This is noted as NVIDIA's first major scale-up of RL in post-training. What is the technical necessity of training on all environments simultaneously?
This is the core technical contribution of RLVR. The problem with sequential RL training is catastrophic forgetting.
Right.
You train on a math environment, and the model improves drastically at math, but then it suddenly degrades its coding skills because the math-specific alignment overrides the general knowledge it learned previously.
So with sequential training, you constantly have to realign previous skills.
Exactly. The RLVR strategy mitigates this by training on all environments: coding, math, question answering, structured output simultaneously. This forces the model to find stable, generalized policy gains that work across all benchmarks, which eliminates those catastrophic skill trade-offs. This stability is all managed by the NeMo Gym and NeMo RL frameworks.
And they implemented a dynamic curriculum training strategy based on sample difficulty using a Gaussian function. That sounds incredibly sophisticated.
It is, and it solves another major RL problem: efficiency. Training randomly wastes time on problems the model already aces or problems that are currently just too hard for it to solve. So they use a Gaussian function to model the target pass rate distribution within the batches.
How does the Gaussian curve manage the difficulty?
The mean of the Gaussian distribution shifts linearly over time. It starts centered on easier samples, those where the model has a high initial pass rate. As training progresses, the mean gradually shifts toward harder samples, those with a low pass rate. This ensures the model is always working in its optimal zone of proximal development. It's challenged, but not overwhelmed.
Right, and this leads to the stable, superior learning progression they observed against random sampling on hard benchmarks like AIM 2025 and GPQAA.
That dynamic difficulty selection prevents overfitting to extremes, ensuring a balanced, stable learning curve. And the stability theme continues into the algorithm itself. They use synchronous group relative policy optimization, or GRPO, with masked importance sampling. This combination handles the complexity of diverse reward signals and is essential for mitigating that training inference misalignment that's so common in RL.
And they brought in an architectural stabilization technique here as well, right? What happens to the MoE layers during the volatile RL process?
To stabilize the policy learning, they made the decision to freeze the MoE router weights during the RL training.
Why freeze the router?
Because the router is the core decision maker for knowledge access. If the router policy changes wildly during RL, the model loses its learned expert specialization structure. By freezing the router, they maintain the structural integrity of the MoE setup, but they still allow continuous updates to the expert bias. This allows refinement and alignment of the knowledge within the existing expert structure without compromising the overall system's stability.
The verifiable environments they used cover a huge range of agent tasks, including structured outputs where the reward is based purely on exact JSON schema adherence. That's a very specific and necessary requirement for agent systems.
Precisely. They also included complex environments like Workplace Assistant, which involves multi-step tool calls verified by database state changes, and multi-turn conversational agents. The focus on verifiable rewards ensures the model is aligned to objective success metrics, not just stylistic preferences.
Okay, the final alignment stage uses RLHF, but instead of a standard pairwise comparison model, they utilized a generative reward model, or GenRM. Why are GenRMs generally preferred for this task?
GenRMs, especially one built on a highly capable base like Qwen3 235B, they just tend to generalize better than traditional models. Traditional preference models often learn superficial indicators of quality, which leads to reward hacking. The GenRM, by generating a reasoning trace before providing a score, forces the model to capture deeper semantic features of helpfulness and accuracy. This reduces the risk of the target model gaming the reward function.
So how does the GenRM output translate into the final reward signal?
The GenRM generates two outputs for any candidate response: individual helpfulness scores on a 1 to 5 scale and a ranking score from 1 to 6 compared to its peers. The final reward function then aggregates these helpfulness and ranking scores and applies a strict penalty I format if the model violates the requested output format.
Scaling RLHF is often bottlenecked by the quadratic computational cost of pairwise comparisons. If you generate, say, n equals 60 responses per prompt, comparing all pairs is huge. How do they slash that cost?
They adopted a highly efficient circular comparison strategy. The computational cost for naive pairwise comparisons is O of n squared, which would mean 120 comparisons for n equals 16. Circular comparison reduces this to linear complexity, O of n, so only 16 comparisons.
How does that look practically?
Instead of response A being compared to B, C, D, and so on, each response is only compared against its immediate successor and its immediate predecessor in the group. This structural change ensures that all responses are connected within the comparison graph, so you maintain the necessary diversity of feedback, but you achieve a massive cost reduction. From O of n squared down to O of n.
Okay, here's where it gets really interesting. The length control mechanism. Models tend to get verbose during RLHF as they generate longer, sort of protective reasoning traces to ensure they hit the reward target. This inflates latency. How do they solve that with the group relative length control?
This is just master-level incentive design. They introduced a novel group relative length control mechanism to counteract that verbosity inflation without damaging accuracy. The mechanism computes a zero mean group relative length bonus.
Zero mean and group relative. That's the key. So they're basically training the model like a team of marathon runners, where the bonus isn't just for winning, but for being faster than your own teammates. Only if you also finish the race well.
That's a perfect analogy. Group relative means the length adjustment is benchmarked only against the average length of the n responses generated for that specific prompt. Zero mean ensures that the group as a whole isn't penalized globally. Only the relatively shorter responses get the bonus, and the relatively longer ones get a penalty. This adjustment is applied separately to the length of the reasoning component and the length of the final answer component.
And the result of this?
They reduced the model's overall verbosity level by 30% during training. Now, if they had simply applied a length penalty to all responses, the model would just learn to output short, low-quality answers. To prevent this, they introduced the quality-gated bonus.
Oh, the gate. You have to be short and good to get the bonus.
Exactly. The length bonus was applied only to the shortest responses that achieved a top-tier quality score, specifically those whose base reward was greater than or equal to the 80th percentile of rewards in that group. It's a sophisticated system that forces the model to maintain high quality while optimizing for conciseness, a powerful combination of behavioral alignment and efficiency engineering.
That post-training pipeline is arguably more important than the architecture itself for the agent use case. It's what delivers the reliable, controllable, and efficient behavior needed for autonomous systems. So we have a fast, sparse architecture, trained on colossal data, and aligned using sophisticated RL. The final step for production is optimizing it for maximum throughput via quantization. Nemotron 3 Nano is released in both BF16 and FP8 quantized versions.
Right. Quantization is essential for production deployment. Moving from BF16 to FP8 precision dramatically reduces memory bandwidth requirements and footprint, which allows for significantly larger batch sizes and higher throughput during inference. The challenge, of course, is ensuring minimal accuracy loss.
What calibration data did they use for the post-training quantization? Did they just stick to standard web data?
No. They used a small targeted subset of about 1,000 samples from the post-training reasoning SFT dataset for calibration. And they found that using the specific reasoning-centric data, which reflects the complexity of the final aligned model, yielded a slightly better accuracy recovery compared to using general or random web calibration sets. It shows a holistic approach where the deployment tuning reflects the model's ultimate use case.
They didn't just quantize everything uniformly, which is often the easiest path. They employed a very specific, selective quantization strategy based on a detailed sensitivity analysis. Why was selective quantization necessary here?
Sensitivity analysis revealed that certain components of the model's architecture are mathematically brittle. They're prone to significant error accumulation when their precision is reduced. For this hybrid MoE-Mamba model, they needed to surgically protect the most sensitive mathematical operations.
Let's focus on the why. Why are the self-attention and Mamba layers specifically so sensitive?
Well, attention layers involve massive matrix multiplications and softmax operations that rely heavily on floating point precision to maintain stability across the entire sequence length. Quantizing those leads to immediate steep degradation in the model's ability to locate and process global dependencies. And similarly, the Mamba layers, particularly the linear and Combi-1D projections that handle the state's space recurrence, they rely on high precision because small errors in recurrent operations tend to compound quickly over time, especially in long sequences.
So protecting the integrity of global reasoning from attention and efficient sequential processing from Mamba dictated the quantization strategy.
Precisely. They kept the 6 self-attention layers in BF16. They also protected the 6 Mamba layers that immediately feed into those attention layers, keeping them in BF16 as well. And furthermore, the Conv1D layers inside all Mamba layers were kept in BF16, specifically to stabilize that recurrent state mechanism.
And everything else.
The majority of the model, the remaining weights and activations, were successfully quantized to FP8. And crucially, the KV cache was also quantized to FP8. The KV cache is a huge memory consumer, especially at 1M-Token context length, so quantizing it yields massive memory savings and throughput gains.
What was the trade-off here? Did this surgical approach successfully maintain accuracy while dramatically increasing throughput?
Yes. The selective FP8 model achieved approximately 99% median accuracy recovery across their benchmark suite compared to the original BF16 model. For example, MMLU Pro dropped only from 78.30 to 78.0. That minimal degradation is a triumph of deployment engineering.
And the throughput advantage is substantial because of that FP8 KV cache quantization.
The throughput gain is direct and measurable. Quantizing the KV cache to FP8 significantly reduces the memory required to store the long context key value pairs, and reduced memory consumption enables the use of larger batch sizes on the same hardware, which is the mechanism that drives the high token throughput we discussed earlier. The selective design proved to be the best configuration, balancing accuracy recovery with peak efficiency gains.
So the model is ready for prime time.
Absolutely. It's available through enterprise platforms, inference providers, and as an NVIDIA NIM microservice. It supports all the popular engines like HF, VLLM, TRT LLM, and SGLang. The engineering decisions reflect a focus on immediate production viability.
Okay, we've broken down the deep mechanics, the MoE Mamba architecture, the engineered data like InfiniByte and RQA, and the sophisticated alignment with RLVR and group relative length control. Let's summarize what this entire effort achieved on the final battlefield, the agentic benchmarks.
Right. Nemotron 3 Nano shows strong leadership in the areas where it matters most for its intended use case: agentic workflows and long context handling. It consistently outperforms key competitors like Qwen 3 and GPT-OSS in these critical categories.
Specifically, where does that agentic edge manifest in the numbers?
The agentic edge is clear in benchmarks like SWE Bench and the Ta-Bench V2 average. On SWE Bench, Nemotron 3 Nano scored 38.76%, which is significantly ahead of Qwen 3 at 22% and competitive with GPT-OSS at 34%. It also leads in chat metrics like Arena Hard V2 and IF Bench, and shows commanding performance in long context, achieving those Ruler 100 scores up to 86.34% at 1M tokens.
The reasoning capability is also highly competitive, even before external tools are enabled.
Without tools, it's really neck and neck with the previous best open model. But the success of the post-training pipeline shines when tool augmentation is enabled. This is where the model truly becomes an agent.
On AME25, a difficult math reasoning task with tools enabled, the model performs near perfect.
On AME25 with tools, Nemotron 3 Nano achieved 99.17% accuracy. That slightly surpasses the 98.7% of GPT-OSS in that category. This just validates the entire complex SFT and RL pipeline that was dedicated to teaching reliable tool-integrated reasoning.
And the model offers crucial deployment flexibility through its dual reasoning modes.
That's right. The default is to generate a reasoning trace first, so enable thinking true, which ensures accuracy on complex problems. However, for quick, low-latency tasks, that reasoning trace can be disabled, enable thinking, false, in the chat template. This gives you the choice between high accuracy with slow thinking and high speed with fast heuristic output, which is vital for real-time applications.
One of the most important takeaways from this entire technical report is the commitment to openness, which goes far beyond just model weights.
This is a major gift to the community. NVIDIA released not only the base BF16 and FP8 model weights, but also the comprehensive training recipe, the training code, and critically, most of the new pre-training and post-training datasets. This includes the synthetic data generation detail.
Sharing the recipe and the data for pipelines like InfiniByte and RQA is invaluable for researchers and enterprises building specialized vertical models. It allows immediate replication and customization.
And that openness extends to the alignment ecosystem. They open-sourced the crucial frameworks used in the multi-environment RL training NeMo Gym and NeMo RL, as well as the NeMo Evaluator SDK. This means developers can not only replicate the benchmark results, but can also customize the model's alignment for their own specialized agents using the same high-performance tools NVIDIA used.
That transparency is what builds trust, especially when enterprises are betting on open models for mission-critical applications.
When you synthesize everything, the 13.3 trillion unique tokens used in pre-training, the complex hybrid architecture, and the detailed RL alignment strategies, you realize Nemotron 3 Nano is really a high watermark for open source efficiency. It proves you don't have to sacrifice speed, control, or intelligence when choosing an open model for agent development.
This moves the industry past that forced choice between proprietary speed and open source simplicity. Nemotron 3 Nano successfully occupies that crucial intersection of complexity, control, and performance. So this deep dive into Nemotron 3 Nano has revealed an architecture that is truly a masterclass in efficiency. The core signal is architectural sparsity, using that hybrid Mamba design to get the intelligence of a 30 billion parameter model with the runtime costs of only 3.2 billion active parameters.
And that efficiency was only unlocked by combining it with monumental data engineering like Infinibyte's conceptual crossbreeding and the two-step RQA generation, plus the advanced alignment strategies of multi-environment RLVR and that brilliant group relative length control mechanism. The core signal is a distinct shift toward open, high-efficiency models optimized specifically for complex, multi-component agent systems where latency and throughput are paramount.
Which leads us to our final provocative thought for you to consider. The successful integration of Mamba layers, mixture of experts, and precise selective quantization demonstrates that the next frontier in AI scaling isn't merely about maximizing total parameter count. It's about mastering active parameter efficiency combined with extreme contextual flexibility, like the 1M-Token context. So if we can achieve frontier intelligence at a fraction of the traditional inference cost, what new computational breakthroughs will this level of efficiency enable as agentic workloads move from the research lab into latency-critical, real-world deployment?
To stay updated on the latest in AI and ML developments, visit our webpage, neuralintel.org, and check us out on YouTube.
Thank you for joining us for this deep dive. We'll see you next time.